We've been doing this course now for almost 2 years, right? We began production on this almost exactly 2 years ago, didn't we?
Yeah, I guess so.
In that 2 years, an incredible amount has happened in research and in industry both. We've captured some of that as we've modified the course from run to run, but there's so much that's going on that we can't capture it all, and we really can't take you all the way up to the leading edge of stuff. But it probably makes sense to introduce you to some of the newest ideas. So what's new in recent months or the last couple of years that excites you?
Good question. But one of the biggest interest topic is System One.
From IBM?
Yeah.
What's interesting about it? What is it?
System One is independent full system of quantum computer. It's including 20 qubit quantum processor. And components of System One is quantum processor and refrigerator and control systems. And good shield from external noises. Actually, it is first generation independent quantum computing system.
What's the difference between that and the research systems we're currently using?
今まではその場所がラボラトリーとかそういうところにしか置けなかったんだけども、欲しい人のところに一応買おうと思えば買える。
So what? They've got it packaged and engineered so that it can be installed at customer premises. That's good. That means that you don't have to send all of your data and all of your programs to IBM and trust that it's not going to get. If we want, we can buy our personal quantum computer, but we need to pay. You got enough money in your wallet to buy one?
Unfortunately, I don't have enough money to buy that one.
All right, so that's important in quantum systems. It's certainly one of the most exciting announcements. IBM made that announcement, in January this year?
Yeah, I guess so.
Yeah.
What is the most exciting topic about quantum computation?
In terms of algorithms? Yep. What's new in algorithms? There's a lot of excitement around applications of VQE, which is the variational quantum eigensolver, which we talk about a little bit in the chemistry our articles in our course. And the other one that's getting a lot of attention is, am I going to get the acronym right? QAOA.
QAOA, yeah.
Quantum Assisted Optimization Algorithm. Is that right? Is that the correct expansion of the acronym, I think? Both of these are, we hope, going to be useful in sort of the short run for work on quantum computers, including noisy ones for the kinds of hardware that we can build currently and in the near future. So we'll see what happens with that. The hard part is figuring out how to use these medium-sized systems in the presence of noise, what John Preskill called NISQ, the noisy intermediate scale quantum computers. Some researchers think that those computers are never going to be able to produce results that we couldn't produce classically. Others are sort of optimistic that we can take large problems and break them down into smaller sub-problems and do part of the computation classically and part of the computation quantumly, I guess you could say, particularly in an iterative fashion. So that's actually an important topic in research, is finding where that real boundary is that makes the systems actually useful in sort of a commercial sense. The work that we were doing 10, 15 years ago, and others even before that, was, okay, assuming the technology works and we can start to build real systems with full error correction and everything, how big does the system have to be useful? And the answers were, wow, these systems are going to be really big, and we're also going to need really good physical error rates even for the systems we're building. But since that time, we've sort of shifted focus in trying to figure out, now that the systems are starting to exist in the real world, what's the smallest system that's actually useful? And I don't think we have an answer yet. I think somebody's likely going to hit some useful spot on that soon.
Mm-hmm.